Now that we know how to take the derivative of many, many functions, what we are going to do is now start applying the derivative. At the end of this lesson, you will be able to determine extreme values of a function on a given interval, using derivatives, of course, and then you'll be able to find the critical number of a function as well. Right, I'm just going to read through this. The derivative tells us a great deal about the shape of a curve without the aid of a graphing calculator. It tells us precisely how the curve bends and exactly where it turns. Once we know how to find a function's extreme values, we'll be able to answer questions such as, what is the most effective size for a dose of medicine? Or what is the least expensive way to pipe oil from an offshore well? All right, our goal for this lesson again is going to be to find the absolute extrema of a function on an interval. And we're not just going to be talking about absolute, we'll also be talking about all extrema on an interval. So absolute or global extrema are going to be the minimum and maximum values of a function. And these are always going to be y values. That's super duper key. You want to star it, whatever. So when I ask you for what is the absolute minimum or what is the absolute maximum, those will be y values. Okay, we're going to explore some absolute extrema here. If I'm looking for absolute extrema, notice that the interval, and we'll always be looking on an interval, from negative infinity to infinity. So pretty much this whole entire graph. If I'm looking at the absolute minimum, so what is the lowest this function ever gets? And my absolute minimum would be the lowest the y value it ever gets to is 0. You will notice when you get to Math Excel, they generally like to have you write that as a point. That would be occurring at the point 0, 0. So if they ask you for that, that's what it would be. Okay, if I'm looking for an absolute maximum, I'm looking for what's the biggest y value that this function will always have. And since I'm going from negative infinity to infinity, if I were to plug a really large number in for x squared, I'm just going to keep getting a larger and larger number. So there's actually not going to be an absolute maximum on this interval. So just none. Okay, and the next graph, notice, although this, we're just going to look at this darkened area here. There's a closed circle to a closed circle, and it just says the interval 0 to 2. So if I'm just looking from 0 to 2, just that blackened area, what is the, first of all, smallest y value the function gets to? And that would be 0. So my absolute minimum would be 0, and again, that would be at the point 0, 0. And then my absolute maximum, if I looked at the absolute maximum, what's the highest y value this function gets to on this specific interval? Notice it's not labeled, but it's happening at x equals 2. So if you plug 2 in for this function, you will get 4. So the maximum y value this function reaches is 4. And again, that's happening at the point 2, 4. Okay, this next one, we're still going from 0 to 2, and notice that there's a parenthesis here, so we are not including, there's an open circle there, we are not including that point at 0. So when on the interval 0 to 2, if we're looking for an absolute minimum, we would say the absolute minimum is going to be 0. However, the function is not defined at that point, so we are going to have to say for an absolute minimum, there is none. Okay, and then again, the absolute maximum, since there's a dot up there just like on the other function, we will have that same absolute maximum. And the absolute maximum will be 4, and it's happening at the point 2, 4. Okay, and then this last one, you'll notice we have an open circle and an open circle. And notice my interval is defined from 0 to 2 with parentheses. So now if I'm looking at that area, the lowest it would get would be 0. However, the function is not defined at 0. And the highest would be 4. But again, the function is not defined there. So there are no absolute extrema for this specific picture. Okay, I just wanted to show you real quickly what could be happening. So we are dealing with, specifically in this lesson, absolute, like the function never goes any lower than that, and the absolute maximum, the function never goes higher than that maximum point. However, we can have something that's called local maximums and minimums, and we'll actually get into it later, what we call those relative. So notice the local ones, they're kind of like hills and valleys, so notice it gets up to a certain point, it comes back down, but then what happens, those are just called local because the function can go higher or lower than those. So the locals are just our hills and valleys in the graph. All right, and I do want you to notice in these ones, if we were looking at derivatives at these places, if you look at all of the local minimums, notice, except for this one because it's at the end of an endpoint, the derivatives are equal to 0. And if I look at an absolute minimum, notice this one was at an endpoint, so we wouldn't look at it. But this one, notice this one happened at a cusp, and we would see the derivative there would be undefined. Okay, and that's going to lead us into using critical numbers to help us find those absolute extrema. We've already studied critical numbers before, and we've always said when we're looking for that critical number, when we were working with the existence of an inverse, we always set the derivative equal to 0, where we are going to add one thing to our critical number now. We're also going to add a critical number if the derivative is undefined. So that's the one new piece of that, because we just saw in that previous one that we had an absolute maximum happen and the derivative there was undefined because there was a cusp. So what we are going to be doing is just finding critical numbers. So hopefully you might even want to pause the video and just try it on your own, but I'll let you decide. Okay, so finding the critical number, we just want to take the derivative and see where f prime equals 0 or it's undefined. Okay, and generally we're going to have undefined if we have a square root or if we have fractions. Okay, so first of all, we have f of x is equal to x squared times the quantity x squared minus 2. So we do know we have to take the derivative first. And we could use the product rule on this one, but I think I'd just rather distribute it to simplify it a little bit first. So if I do that, I'm going to get x to the 4 minus 2x squared. And now from here, we're going to have f prime of x is equal to 4x to the third minus 4x. And then from here, if we want to find the critical number again, we're going to set it equal to 0. So I'll have 4x to the third minus 4x is equal to 0. I'm going to factor out a 4 and an x, which is going to leave me with x squared minus 1. And then I notice that this will factor a little bit more. It'll be 4x, x plus 1, x minus 1, and it still equals 0. And now using the 0 product property, my critical numbers are going to be x equals 0, x equals negative 1, and x equals 1. Okay, the next one, again, we're finding the critical numbers, and I can already tell you one of our critical numbers, we are going to have to look for where it's undefined because we're going to have a fraction. Okay, on this one, to get the derivative, we will use the quotient rule because we have a quotient. F prime will equal 2, g prime will equal 1. And now setting up the quotient rule, we have f prime times g, 2 times x plus 3 minus f times g prime, 2x times 1, all over g squared. And now continuing to take the derivative, I'm just going to simplify. I'll get 2x plus 6 minus 2x over x plus 3 squared. And just combining those two x's will cancel out, so my derivative will equal 6 over x plus 3 squared. Okay, we want to find out where the derivative equals 0 or it's undefined. So if we're looking for where the derivative equals 0, we would be concerned with the numerator equaling 0. And 6 will always be 6, so it's never going to equal 0, so we won't have a critical number dealing with the derivative equaling 0. But if I wanted to find out where the derivative would be undefined, that would be where the denominator equaled 0. So I'm going to take x plus 3 squared, set it equal to 0. I'm going to square root both sides. I'll get x plus 3 equals 0, and then solving for x, I'll get x equals negative 3. So that would be the critical number of this specific problem. Okay, and then let's do a trig one. If I have f of x equals sine x plus cosine x, we're going to be limited between 0 and 2 pi, so we don't have to keep going around the circle lots and lots of times. First thing we're going to do is go ahead and take the derivative. And since we have a plus sign, we can take the derivative of each part separately. So I'll have the derivative of sine x is cosine x, and then the derivative of cosine x is negative sine x. And again, looking for critical numbers, we don't really have to worry about it being undefined because we don't have any fractions or square roots. So I will just take the derivative and set it equal to 0. And when I do that, that doesn't really help me. So I'm going to just try something. I'm going to add sine of x to both sides. So I'm going to get cosine of x is equal to sine of x. So now we just need to think on the unit circle, where do the cosine and the sine equal the same value? And I know that our values of pi over 4, both of them equal the square root of 2 over 2. So if you think on the unit circle, at pi over 4, both the cosine and sine would be the exact same value. Over in the second quadrant, one of them's positive and one of them's negative. Down in this third quadrant, both of them are negative, so again, we'd have the same thing, and that would be at 5/4 pi. So my two critical numbers, and then over here, that wouldn't work either because one of them's positive and one of them's negative. So my x value, my critical numbers for this one would be pi over 4 and 5/4 pi. So hopefully now you are familiar with what an absolute extrema is, what a local extrema is, and how to find critical numbers once again.